Hey students, let's go ahead and go through the solutions to exam number 2 here for Physics 122 and use this as an opportunity to self-grade as well as correct or understand each of your mistakes so that you don't make those mistakes again moving forward. It's a great learning opportunity here. So let's talk here. We've got 4 wires. They're connected together as shown. They each have a diameter of 1 millimeter. They each have a length of 8 meters. What is the total equivalent resistance for this configuration from A to B? Maybe I'll write it this way, that maybe I'll just think of this copper wire as being made of a resistor. And then if you kind of look, it hits a node right here and splits into the tungsten and the platinum. And so they're in parallel. Then it looks like the current would regroup together and then go through the lead. And so another way, I guess, of looking at this, and hopefully this is kind of what you did first, is said that I have a circuit here, and it's an equivalent circuit, and I need to find out the equivalent of these 4 resistors. Let's start by finding out the resistance of each individual one. And so let's call this one R1 for the copper, R2 for the tungsten, R3 for the platinum, and R4 for the lead. So I guess for the copper, it would look something like this, where we need to look up the resistivity. So going back to chapter 27, and I believe it's table 1, looking up the resistivity for copper is 1.7 times 10 to the minus 8. And then I can multiply by 8 meters and then divide by the cross-sectional area. Now they did give me diameter, so let's make sure I cut that in half. So 3 zeros would be a millimeter, and then a 5, and then I'll square that. So this would be the resistance of our copper piece. Okay. So grabbing my calculator here, 1.7 times 10 to the negative 8 times 8 divided by a pi, also divided by 0.0005 squared, gives me a resistance of 0.1730. So not much as to be expected. It is made out of copper after all. But we can do the same logic for number 2, number 3, and number 4. And maybe saving our little time, especially on an exam, we'll see that this is resistivity of 5.6 times ... and everything's the same. This is 11 times ... and everything's the same as the copper. And this is 22 times ... and everything is the same. So to save myself a little bit of work, why don't I just take the number that's already in my calculator, get rid of the 1.7, so divide, and then multiply that by the 5.6. So it looks like this is going to be a 0.570 ohms for number 2. Now for number 3, let's undo the 5.6 multiplication and replace it with times 11. So this is about a 1.12. Actually, it looks like all these other numbers come out, and that's the same multiplication factor. There's the 1.7, there's the, 5.6, 5.7, there's the 11, so this is probably a 2.2 something. To give it a try here. Divide by 11, multiply by 22, 22.4 or 2.24 ohms. All right. So here is our 4 resistors. And of course, we're asked to find the equivalent. At least that's the first question. It looks like there's a question there and a question there. All right. So maybe I'll jump up here so I can save the bottom half for part B. But it looks like the 2 and the 3 are in parallel. So let me find that equivalent. So I'll take the reciprocal of 2 and the reciprocal of 3 and take the reciprocal of that. And remember, we said that the math meant that the overall resistance will be smaller than the smallest. So we should be under 0.57 here. So 0.570 reciprocal added to 1.12 reciprocal, hit enter, take reciprocal of that. And it looks like we're about a 0.378 ohms for the equivalent of these two. And I don't know, maybe a different color will help it stand out. But now that I'm thinking of these two as one, then 1 and this equivalent and 4 all in series. So I can just add that for the equivalent of all. Maybe I should have put equivalent of 1 comma 2. No, that was 2 and 3. 2 and 3. All right, so I'm going to add them all, and since this one's already in my calculator, I'll start with it, and then go back to number 1, 0.173, and the last one, 2.24, has the most resistance, and I guess the first answer would be 2.79 ohms. So the equivalent of all of those is 2.79 ohms. All right, so then when we jump into part B here, part B says if the battery with an EMF of 1.55, you might remember that one from the lab, the energizing batteries, and no, they were Duracell, sorry, 1.55, and an internal resistance of 0.75 is connected between A and B, what is the current that flows in the tungsten wire? All right, so based on that description, I'll put an EMF of 1.55 volts, an internal resistance of 0.75, and then the equivalent of these 4 wires is the 2.79 ohms. And that's extremely useful because I have 1 voltage, 2 resistors that are in series that I can just say the resistance total is just adding them. And I can get to the current going through here. Now, that's not quite the full answer because this equivalent resistor represents it flowing through here and then branching off. And so let's have some more discussion here. But it looks like this is going to be the total current, and then the amount in the tungsten branches off a little bit. So 1.55 divided by 2.79 added to 0.75 gives me a current of about 0.438 amps that comes out of the battery, and in this case goes through resistor number 1, and then we got to figure out how much splits here. Now there's a lot of ways of doing that. We could write some loops, but I think probably the easier way is at this moment just think about these two as being 1. See, because that 1 is this much resistance. So if I wanted to do the voltage here, V equals IR, and again, thinking of this as 1, all the current would flow through there, so that'd be 0.438. And its resistance of those two together is 0.378. This will give me that voltage across this parallel piece. So times 0.378 is a voltage of about 0.166 volts. Okay. Now, then finally, I can get the amount of current in the tungsten, because I would say that that voltage is the same as, both of them. That's why they're in parallel. And so looking at just number 2 here, just the tungsten, I have this voltage, 0.166. And if I then divide that by the resistance of the tungsten, 0.57, then I'll get the current. So divide by 0.57, and it looks like 0.290 amps is the answer to B. So answer to A is here, answer to B is there. All right. Hopefully that was useful. Let's see. Let's try number 2 now. So number 2, we have this circuit, excuse me, and we are asked to find the current, the voltage, the power in each of these resistance. It's a little more complicated circuit in the sense that it's got 3 batteries, and we got batteries battling each other. But the real key to this is to recognize right away that nothing is in series and parallel. So unlike problem number 1, we cannot do this by equivalence. So we're going to go to the fundamentals, which is the Kirchhoff's loop and node rules here. So pick and label a current, as we said. And you probably heard me say that I like to kind of guess the direction of the current, but not too hard, because remember, if we get it wrong, we'll just get a negative number. And so I'm going to say that current number 1, being from the bigger battery, looking at these other ones, even though it's fighting against this 1.5, is going to win, even though it's going to lose some energy here. It's going to battle through. And I'm pretty confident in that one, because if it was the other way around, this one would have to battle through and then lose that and still be stronger than 6. So it couldn't do that. So I know this one's going to be right. Now it hits this node, and again, I'm pretty confident that there's nothing to battle against. Current number 2 is going to go through that resistor. It's number 3 that I got to wonder about, because number 3 has been weakened, or excuse me, number 1 has been weakened, and it's fighting against 2 volts here. But it's 6, and it loses some here, voltage, which I don't know yet because I don't know the current, so some IR loss there, another 1.5 volts. And so is it over 2 by the time it gets here? And I'm going to say perhaps so. No, I'm going to say perhaps not, just yeah. I don't really know. I suppose we could spend some time analyzing the numbers a little bit more, but that's exactly what I'm trying to avoid, is not really spend too much time avoiding it. I'm just going to say this one kind of wins out. I kind of want to go the other way now, but I already drew it on there. But the point is, we could sit here and spend a lot of time kind of analyzing it to see which way it is, but it's not needed, because we'll just write out the equations. If we get a negative number, it just means the current goes the other way, and really that says what we are doing here is labeling the current in terms of 1, 2, and 3, but also what's the positive direction, and there's nothing wrong with a negative. So there's no reason the current can't go opposite of what we call positive. It's like having a baseball. You have the x-axis. There's no reason the baseball can't travel in the negative direction. When you pick your x-axis and you pick positive, you're not saying that's the direction it travels. You're just saying, this is what I'm going to call a positive direction, and when I work out the problem, I might get a negative. Anyways, same thing here. All right, so with that in mind, let's do our 2 small loops. And so maybe I'll start down here in the lower left-hand corner and go plus 6 as I go in a clockwise direction, minus 100 I1. I'm going through the battery from the big to the small, so that's a decrease of 1.5. And then here I'm going with the current, so that's another negative, and the resistance is 200, and it's I2, and that gets me back where I started. So there is the loop number 1. which I'm going to eventually write as an equation here in a matrix. But let me write out equation number 2. Again, let me start in the lower right-hand corner. This time, let me go counterclockwise so that I get a plus 2 minus 300I3 minus 200I2 equals 0. Be back where I started. And that's the 2 loop. So that's 2 of our equations. And remember, we need 3 equations. And remember, we have 2 small loops, so we can only get 2 independent equations from the loops. And so, in other words, don't do a big loop. A big loop mathematically is nothing more than the sum of these two. Or I guess in this case, the difference between these two, because I did one clockwise and one counterclockwise. And then the node is the conservation of charge, where what flows in equals to what flows out. And the way I've done it, it looks like number 1 and number 3 are flowing into this node, and then number 2 is flowing out. And so now let's go ahead and write this as one big matrix equation. And then let our calculator reduce through a bunch of mathematical operations to an identity matrix, and then we will get our answer. All right, so why don't I rewrite this equation, and I'll just kind of do it mentally and move these to the other side. So this would be a plus 100 and a plus 200, and no current number 3 is in that equation. And then on this side would be 4.5. Okay. This equation, again, if I mentally bring it over here, would have a 0 for current number 1, a 200 positive for current number 2, a 300 positive for current number 3, and would remain with a 2 on this side and a positive 2. And on this one, maybe I'll just imagine bringing the current number 2 to that side. So that'd be a 1, a negative 1, and a 1. And so if we multiply that out, that would leave with 0 on the other side of this equation. So there's my matrix equation. And so let me, let's see, how do I get to my matrix? Well, let me set this in the screen here. So I'll go to my matrix, I'll go to edit, and I'll go 3, 4, and I'll enter a 100, a 200, a 0, and a 4.5. So that's that first row. Then I'll go 0, 200, 300, and 200, and then a 1, negative 1, 1, and 0. All right, so matrix A, 100, 0, 1, 2, 2, 2, negative 1, 0, 3, 1, and the last column, 4.52, 0. Okay, so I'll just go quit. Now, if I go about my matrix equation, I want to do some math on there, and the math is that reduced row echelon form. So I want to apply this operation, and what that will do is manipulate it till I get to the identity matrix. I do need to select my matrix. All right, so I'm going to do an RREF on matrix A, and okay, there's the identity matrix, and so this becomes 0.168, 0.141, whoops, 141. And, interesting, this is a negative. And so the current's coming back here, depending how we want to label it, Doesn't really go this way. It does veer off and kind of have a small value trickling through here. So I don't know if I want to change my direction or just put a negative in the answer here. Probably I'll just put a negative. So let me not change that. But I'll keep in mind that we are actually charging this 2-volt battery as well as charging this battery, assuming they're rechargeable batteries. It could just be heating the batteries, but we're not using the energy in the battery. This battery is using it and forcing it through in the what you might call the reverse direction. All right, so 0.08, 0.168, 0.141, and negative 0.0027. And let me just emphasize, for the answers, the negative is not really important. If you want to label it positive, hopefully you would change the direction there. But that's not a big deal either. Now, when I look at the voltages, I could just say, all right, this is the current times the voltage, right? Anytime you know any of these two, you know the third. So this would be 1.68 when I multiply by 100. This would be a 282 when I multiply by 100 and double. And this 0.0075 times 300 is 81. And again, we could put a plus or a minus. I'll just leave it as a plus here. Okay. So there's the voltages. Now to get the power, again, we have all kinds of options. Current times voltage might be the easiest, but we could go V squared over R or I squared times R. But I'll just multiply those two together. So 0.168 times 1.68 gives me I just noticed that I was a little careless, and I'm sorry. Whoa. This was a 0.0, and that totally makes sense. Did I do that one? Ah, and I did do that one. Yeah, I didn't... like how the numbers didn't match. Okay. 0.01. That way, when I move it to 2, otherwise it would add it up to way more than 6 volts. And I didn't move my decimal right. All right, so I kind of... anyway, somehow, I had this 0 in my head correctly, and I got the voltages right, but I forgot to write them correctly here. All right, let me fix all that. So I think I have the current right now. Okay, so 0.0, and then when you multiply by 100, and then we multiply by 100 and double, and then multiply by 100 and triple. Okay, good. All right, so let's try all that again, because it should be 0.0168 for the current, and times 1.68 for the voltage. So 0.0282 for the power. Much more reasonable number. Okay, so 0.0141 for the current, and then times 2.82 for the voltage. So 0.03, I'll call it a 98. And finally, this last one, 0.0027 for the current and 0.81 for the voltage, 0.00219. Okay, good. All right, so there was quite a bit on that problem. Now, let's get to our RC circuits. And so another thing we did in Chapter 28, but besides those advanced multiple batteries and multiple resistance circuits, is we did our capacitors. Now, the good thing about it is we actually already solved, and so I'm going to use that as my springboard for when they're charging up. There'll be like a total charge it will get to N1 minus the exponential decay of the time and the RC time constant. So that's what happens when it's charging up. And then, of course, we also did when it's discharging. And we had almost the same equation, so we ended up with almost the same results. And I list both of those because when we study this circuit and it says switch to A, you can see that the current then is going to run through the 10K, through the capacitor, through the 15K, and then complete the circuit. And so for the first part of this question, I'll call it part A, the capacitor is charging up. And so we'll be looking at this equation. But the second part is then after this has developed a charge, and so it does say here in part A, how much time does it take to reach 9 volts? Because then when we reach 9 volts, it says then when the capacitor reaches 9 volts. So in other words, not completely charged, the switch is then moved to B. And so when we move to B, now the capacitor is going to discharge. And this branch is useless or isn't doing anything. So when it's at A, we can ignore the 25K resistor, and then when it's at A, we can ignore the battery and the 10K. All right, so let's go ahead and talk about during the charging process. You might remember then capacitance is charge times the voltage, because it might be nice to work with this one by multiplying then no, let's divide. Voltage is charge over capacitance. Yeah, let's do that and divide. That way we can talk about the voltage as a function of time. And then this would be the maximum voltage if you just left it there indefinitely. And we know that if we left it there indefinitely, it would build up to 12 volts. So I can put 12, and I'm waiting for it to get to 9 volts. And that's the question, how much time it would take. Now, another part of this is to remember, we did a problem like this, and there's a little subtlety here, but even though these two resistors are not next to each other, because it's a loop, they have the same current. And that means they're in series. In fact, this whole thing is in series. This resistor is in series with this capacitor, which is in series with that resistor. And if you were writing out a loop, you would have something like this. You would, have 12, and you would minus your 10K times the current. Then you would do the voltage on the capacitor. But then here's the big one, minus 15K times the current. And my point is, whether or not these two resistors are right next to each other in the circuit, if they're in series, they're going to have the same like terms somewhere in our equation when we go to solve it. Now, we don't have to solve it because we already did that in class and in the textbook, but the point is I could think of these two as being in series. And so this resistance is 25,000, and the capacitor is 25 millionths. And so that right there is what we called the time constant, the RC time constant. And so grabbing my calculator, 25,000 times 25 micro is 0.625. And so I can replace all of these with this 0.625, and I think I will. although I think I will move the 12 over to here also. So this is a 0.75, and then we've got a 1 minus e to the minus t over 0.625. And now maybe I'll move the e over to the other side, and the 1 minus 0.75, which is 0.25. And of course, now if I take the natural log of both sides and eventually solve for t. All right, so let me take the natural log of 0.25, and it's less than 1, so that ought to be a negative number. And that's good because I want to take the negative of this here. And so, in fact, maybe I will do that. So times a negative 1 from here. And then multiply by 0.625, and I get 0.866 seconds. All right. So not quite 90%, but I'll just call it 90%. So if we close this for 90% of a second, or maybe 87% of a second, this will have built up, this capacitor here, to 9 volts. And so there is A. Now in B, what we're going to do is throw the switch the other direction, and it's going to begin to discharge. It says, so when the capacitor reaches 9 volts, the switch is moved to point B. Well, what is the voltage across the 25K? And so now it's discharging, and it's going to go through the 25, but remember the 15 is in series with it. So this is going to be a 40K after 1.5 seconds. So we have a different decay rate. Our RC is now 40,000 times 25 times 10 to the minus 6, which 25 times 4 is 100, and then we've got 4 zeros and 10 to the minus 6, which is nice because that makes an even 1 second. All right, so we've got a larger decay constant, and rightfully so, because we're going through more resistance on the discharge. And last time we were 0.6 seconds. All right. Meanwhile, we are going to discharge, and I'm going to use this equation for the discharge. But maybe the thing to do is to take its derivative, because the derivative of the charge coming off of the capacitor would then be the current coming off the capacitor. Taking the derivative then here, this would be that initial voltage divided by the resistance, and so that's going to be the initial current coming off of the capacitor. And so let's take a moment to think about the initial current. Because if we do a loop right here, and I'll start on the lower right-hand corner and we'll do a loop right here, plus 9. But then we're going to go minus, and I'll just think of these two as 40,000 times the current, and I get back. So in other words, the initial current is, of course, the initial voltage divided by the resistance. So this is 9 divided by 40,000. And so we're looking at 2.25 times 10 to the minus 4. And that's what I'll put in here. And so the current is 2.25 times 10 to the minus 4 e to the minus. And it says what's the current after 1.5 seconds, with our decay constant being 1 second. So let me take that and multiply it by e to the negative 1.5. And we're looking at a current of 5.02 times 10 to the minus 5 amps. Okay? And so we're almost done. One more small step, because it asks for the voltage. And to get the voltage across just the 25, because remember, this right here is the whole voltage on the capacitor, which is the voltage on the two of them. We've got a fraction of that. So we've got this current that's going through our resistors, both of them, but in particular the 25,000 one. And so I'm going to take that current and multiply by 25,000, and that should give me a voltage of, it looks like 1.26 volts. Yay! Okay. So there's number 3, and kind of ending our 2 chapters on circuits. Because as you know, we then went on to, that was chapter 27 and 28. Yeah, 27 and 28. And so in 29 and in first part of 30, and this actually is the first part of 30, we got into our magnetism. And we had that Biot-Savart law, and we worked out straight lines and loops. So I'm going to suggest you start there. The straight lines, the magnetic field was the permeability of free space times the current. 4 pi a, where a is the perpendicular distance. And depending on which way you write it, sometimes we write it as sine of an angle, and other times we write it as cosine of an angle. I'll go ahead and do the sine one, and I'll think about that being applied to this straight piece right here. Because I do have another piece to worry about, and that's this arc. And because we've got this counterclockwise loop, and they give us the current. But let me just start with this straight piece, and let me just say they're trying to find the magnetic field here at the origin. So the perpendicular distance is right here. And maybe if I kind of switch my paper, it'll look more like our derivation, where this would be 45 degrees and this would be negative 45 degrees. So I'm going to put sine of 45 degrees and then go sine of negative 45 degrees. If I put in my permittivity of free space, and I didn't really give myself enough room for the current. Let me squeeze it in. But then I have this distance A, and then reading these dimensions, this is 2 centimeters. So halfway would be 1 centimeter. And then, so this would be 1 centimeter times root 2. Or you could say 1 centimeter divided by cosine of 45, which I guess there's a lot of ways we could do this. But I'll just take it then as 1 centimeter times the square root of 2 for the perpendicular distance away. In fact, I'll even simplify this because sine is an odd function. So I can take that and put it here and make a plus. And so this is 2 times sine of 45. And I'll even cross out these 4 pi's, making my calculator work a little bit easier. So across the top, I'll do 1 times 10 to the negative 7 times 5.25 times the 2 times the sine of 45. Then I'll divide that by 0.01, as well as divide it by the square root of 2. And I get 5.25 times 10 to the minus 5 for the magnitude. Because maybe now I should take my right hand and pretend I'm grabbing the wire with my right hand, so my thumb is in the direction of the current here. And so my current is pointing down here at a 45-degree angle. But looking at my fingers on this place that is to the, I'll call it southwest of the wire, my fingers are pointing inward. So this should be inward, which I'll represent as a negative z direction. So this would be the magnitude from the straight wire. I'll just say straight. Now, the other thing we were working with was circles, loops, and we had the equation for a full circle that looked like this, where r is the radius of this circle. We don't have a full circle, we have a quarter of a circle. So I'll put a little factor there. So we have 4 pi times 10 to the negative 7 for the permeability of free space, the 5.25 for the current. The radius is 0.02. That was given in the problem, the 2 centimeters. And then we have the 4, which, grabbing a calculator, maybe I'll just put it down here. I have my, clear that calculator, 4 pi times 10 to the negative 7 for the permeability of free space. Then the current, 5.25. Then divided by a 2, then divided by the radius of 0.02, and also divided by a 4, gives me my 4.12 times 10 to the minus 5. Now again, we should point out direction, and using the right-hand rule again, so the thumbs up one. But this time letting our fingers be the currents and holding our right hand so our fingers curl with the current. So the current is going in a counterclockwise direction. So I'm going to hold it so my fingers are going in a counterclockwise direction. And my thumb is up, out into the screen. So that would be a plus z direction. And so the thing to recognize is that our two fields are opposite in direction. So hopefully you noticed that there was a magnetic field created from both configurations, both the straight line and the arc. And so now you calculated them. But the last big piece is to recognize that to get the total field, we have to combine those two. And it's what we would call a vector sum. That is, you have to worry about their directions. And so sure, one is positive and one is negative. And so I would have B total then being the 5.25, and I'll just say over here times 10 to the negative 5. I'll even put the negative with the number and call that a k hat, because the other one is a plus k hat. And so it's times 10 to the minus 5 times k. And then it's 4.12. So it looks like if I subtract those, I've got a 13 and a 1 and a negative. and then times 10 to the minus 5, and in the z direction. So there, finally, is the total field. So 2 fields, one from each configuration, an arc and a straight line, and then adding them together, doing a vector sum, gives me the total field. Nice. So hopefully that one went well for you also. And now to our last problem, and our second one on some magnetism. And it starts off with just the force on a moving charge. So that was kind of the very first thing we did when we got to magnetism. And so this is right out of chapter 29. It says this long wire has a current of 15 amps. So I'll put that. It's moving in the negative x direction. We have an electron that is 1 centimeter from the wire and is traveling in the positive z direction with a speed of 2.33 meters per second. What is the magnitude and the direction of the magnetic force? So why don't I just start with, say, magnitude. The magnitude here would be Q times V times B times the sine of, and it looks like this is going to be 90 degrees. This is where we're going to have to do a kind of a little bit of work, and I'll go to my green, but if I do that right-hand rule with my thumb in the direction of the current on these places here where the electron is in front of the wire here, is then making an upward field of B. And of course, V is coming out, so doing a... Oh, I started to get into direction. Let me hold off on that one. I just wanted you to see then that V and B are 90 degrees. Then that's where I'm going to get that 90 degrees. So again, just focusing on the magnitude, I won't worry about any direction or positives or negatives. So the charge on the electron, without worrying about the negative, is 1.602 times 10 to the negative 19 coulombs. The velocity, again, not worrying about any kind of positive or negative here, is 2.33 times 10 to the 5 meters per second. Now, the strength of the field is where we get into a long straight wire, and so this is where a little bit of chapter 30 comes into play, where it's the permeability of free space times the current over 2 pi times the distance away, which they say we are 1 centimeter outward. And that would be in units of Tesla, which I can write as a Newton per coulomb per meter per second, so that the coulombs cancel and the meters per second cancel, and we're going to get a force. So there would be the magnitude of the force. So 1.602 times 10 to the negative 19 for the charge, 2.33 times 10 to the 5th for the velocity, times, and I can save a little bit of calculator buttons. But remember, the permeability of free space is 4 pi times 10 to the negative 7. So when I cancel with a 2 pi, I'm just left with 2 times 10 to the negative 7 for that one. And then I don't have to worry about the 2 pi down here. The current is the 15 amps. And I still need to divide it by the distance away. And so not much of a force, but again, this is a little tiny electron. And so this is 1.12 times 10 to the negative 17 newtons for the force. Now to change it to a vector, that is, what direction is it? Because it says what is the magnitude. So I did the magnitude. And the direction, I need to do this cross product. And as we said earlier, the magnetic field is going up at this location, and the electron is coming out or towards the screen. And so V cross B would be putting my fingers, maybe towards U and crossing it upward towards B. And so that's my V cross B. And then I would multiply it by a negative because it's an electron. And so it would be along the X direction here. And so I guess that would be labeled as an I hat direction. And let me just double check that. Something's bothering me about it. Let's see. So right hand, B is up, V is out. So V cross B is in the negative X direction. So an electron would be the other way. Okay. All right. And so this electron is going to be pushed towards the x-axis. So its motion as it's moving out would curl towards the x direction. And that is probably the easier of the two. It's got a lot of pieces to it. Here's kind of the hard one, although it does match a lot like the practice exam, although the practice one you had a straight sheet. This is bent, but actually the math comes out a lot easier now that it's bent. So let's see what we get for the total field when we have this half a cylinder with the current. Because it says then this long wire, still having a current of 15 amps, is reshaped into a long, thin, hollow half cylinder with a radius of 2 centimeters. What is the magnetic field from this current at the center? So let me draw kind of a cross section. He'll be the center. He'll be a semicircle with, kind of the current coming out. So I'm going to think of this as a current coming out, and another little chunk, current coming out, and another little chunk, current coming out, current coming out, current coming out, current coming out. And I won't draw all of them, but I will use my right-hand rule here to say that if I were to grab, say, this lower one right here, and point my thumb coming out of the screen, my fingers would curl around in a counterclockwise direction. And so the magnetic field from this one alone would be pointing downward. Now, in general, so I can add all these up, that is, so I can do an integral, maybe I'll look at this one. And so this one, I would again point my thumb coming out, and the fingers would go around, and so I would be making a field kind of in that direction. And so if you kind of imagine everywhere along the points, you would have something that would look like this. You would have a field from the first one like this, and then 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 like that. And so we would add all of these up. Now, the reason that can be helpful is just by looking at this picture, you can kind of see a symmetry that for everyone pointing to the right and down, there's another one pointing to the right and up. And so because of that, I might start off by saying the magnetic field in the y direction is going to be 0. It's going to just cancel off. There's no point in setting up an integral and doing a complicated calculation. That's it. Now, the x direction doesn't cancel off. And so we might start our calculation something like this and say, okay, the total in the x direction is adding up a little bit of x direction from each little bit of piece, and then we're going to add up all those different currents. And so drawing this one, I might think of it as a little bit in the y and a little bit in the x. And so right there is my dB sub x. Because this right here would be just my dB. So this is the magnitude. So if this is some kind of angle, let's call it theta, I would then be saying, if I take the magnitude dB and multiply by sine of theta, that's how I get the x component. And for a long straight wire, we can say dB is this thing, right? This is the equation for the magnetic field from a long straight wire. And so you might say for this, one microscopic wire right there, this is mu naught times the microscopic current that's going through here over 2 pi, and its distance away. And I guess I should be a little careful because in this problem we were looking at 1 centimeter away, but I believe this was a little different. Yeah, it was 2 centimeters, so 0.02 is the distance away, and then we have sine theta. Okay. Now, let's talk a little bit more, and in particular, this little bit of current. Maybe I'll do that over here. But you could say then, in proportions, that if I took the whole current around this semicircle, which is current I, that's our 15 amps, and divided it by its length, which would be pi times 0.02, because remember the circumference of a circle is 2 pi r, so I'll just take half of that. So this would be the whole current divided by the whole arch, would equal a little bit of current along a little bit of arch. And so I'll call right here a little length ds. And that's nice here because I can now replace this di with I over pi times 0.02. And so that's these two together. Oh, and then my ds, sorry. I not forget the ds. I got to bring the ds over there. Okay. Now it's getting kind of messy inside of my integral. So maybe I'll start pulling things out that don't change, that are constants as I add up around this semicircle. So I'll pull out the mu naught. I'll pull out the total current. Down in the bottom, looks like I'll have a 2. Looks like I'll have a pi squared, and I'll have the radius squared. So pi squared and radius squared. And I got an integral of ds sine theta. Now, the theta that I've been talking about is this theta. But maybe drawing a bigger picture can be helpful here. So here's a semicircle. And so here's a vertical line. And so here would be, say, the magnetic field, the dB, and this is the angle I've been calling theta. But that is the field that comes from this little bit of current di that has been spread out over an arc of ds. But what I want you to see then is that this would be that same angle, because this would be 90 minus theta, and then this would be theta again. Or you can imagine kind of swinging an arc. If you started here and swung it up, then this, as this swings over theta, this swings up theta. And so I could change my thought process from thinking of theta as this angle to thinking of theta as that angle, because we know that the arc of a circle is the radius of the circle, which in our case is 0.02 times a little bit of movement of this arc, d theta. And those are the same angles. And so I could then replace this. So mu naught I over 2 pi squared 0.02 squared, and I'll have an integral and replace ds with 0.02 d theta sine theta. And now we got a very easy integral to do. And so this is mu naught I, and I'm just going to take that 0.02 and cancel with it one down there. So this will be 2 pi squared, and we'll still have one of the radii downstairs. But then I just have an integral from 0, and so maybe coming to this picture, 0 on up, all the way around to pi. And the integral of sine theta is minus cosine theta, evaluated from 0 to pi. And I could squeeze it on here, but let me just keep writing down here. So then this would become a 4 pi times 10 to the negative 7. Current, 15 amps. 2 pi squared 0.02. And then right here would be the negative of the cosine of pi minus the negative of cosine of 0. And that's nice, because cosine of 0 is 1, and those two negatives make a positive, so all of this is a plus 1. And then this is also a plus 1, because a negative of a negative 1. And so that's just a 2. And so what I have is this 2, I guess, technically, up here in the numerator, would cancel with that 2. So now I can grab my calculator, and I'll just do the 4 pi times 10 to the negative 7 times 15. I already canceled that 2. Divided by, I already canceled that 2, but it looks like I've got my pi squared, and it's like also divided by 0.02. All right, so after all of that, I get a field of 9.55 times 10 to the minus 5 Tesla. Yay! And done with the hard one. Okay, hope that was useful. Take care, everybody.